Hi and welcome to the video. So in this video we're going to be solving the maximum contiguous subarray problem, and the problem statement is as follows. So we want to find the contiguous subarray, and contiguous basically means if you have an array, let's say A1, A2, A3, A4, and A5 for example, an array that has 5 elements, then a contiguous subarray is basically a subarray of this array which is connected. So for example, I take any I and I take any j, then where I is less than j, and then I say AI plus 1, AI plus 2, and so on all the way to aj is a contiguous subarray of A. So we want to find a contiguous subarray within an array that has at least one number and which also has the largest sum. So for example, given the array -2, 1, -3, 4, and so on, the contiguous subarray for -1, 2, 1, this one here, over here, has the largest sum, which is 6. So how do we solve this problem? Well, one possible idea we can think about is, let's draw the array here, right? Let's try and visualize the array. So we have A1, A2, A3, all the way to AN, okay? So one possible idea is we can calculate all possible I-J pairs, okay? So I have two loops, one looping for all the values of I, and another loop looping for all the values of j. And then I basically check the sum between AI and AJ. I check that sum. Let's say that sum is current sum. Right? So I calculate current sum for every single pair I and j, and then I update a maximum, so maximum sum, a global maximum sum, which initializes at 0, and then I update it with the maximum value of all these current sums. So how would that look like in pseudocode? Well, one possible way is for I1 to n, right? And then for j 1 to n, and then or I, so we wanna I less than j, so we start from I plus 1. So for j, I plus 1 to n, then I go for k, I to j. So I'm going from k to j, and I have a current sum here, current sum as 0, and then I say current sum is equal to current sum plus ak. And then once I'm finished with this loop here, then I say I have a maximum sum outside, which I initialize to 0, and then I say maximum sum is simply the maximum of the previous maximum sum and the current sum. So if I can somehow manage to get the maximum of this current sum, and then once I'm done for all the pairs, then I simply return maximum sum. Now, this solution, this loop here takes O of n time, and this loop takes O of n time. Simply this I could at worst case be 0, and this j could be n. So this loop at worst case might take O of n time. So this whole process ends up being an O of n cubed solution, right? And you can actually, you can start doing some optimizations. For example, you might notice automatically that you don't need this loop, so you can start pre-processing another array, which is A1, A1 plus A2, A1 plus A2 plus A3, and so on. And then if you want to find the sum from AI to AJ, then it's simply the value of let's say if this vector is V, then it's simply Vj minus Vi. So you can get rid of this step in O and do it in O1, but that's still an O of n squared solution, right? So in this video we're going to be basically explaining a dynamic programming based solution And the first idea we'll say is it's going to be an ON squared solution, right? But we're going to notice a certain pattern in the solution, and then we're going to take it down the dynamic programming all the way to O of n. Okay, so it's usually very useful when you're solving a dynamic programming problem to define VI, right? VI as the maximum. So we'll define VI as the maximum sum of a contiguous subarray. So I'll write that as subarray, which ends, okay, so this is very important, ends at the ith element. So what does that really mean? Okay, so I have my elements here, A1, A2, A3, all the way to AI. So I'm saying that VI, my VI, should represent the maximum sum of a contiguous subarray that ends at the ith element. So this is included here. And then there's some I here, right? Some I in the middle, so AI here. There's some I in the middle here, where this sum, contiguous sum, is the maximum contiguous sum for any subarray ending at AI. So for example, if I do AI minus the sum of from AI minus 1 all the way to A, so this is AI minus, so AJ here, yeah. So the sum from AJ minus 1 all the way to AI is always less than the sum from AJ all the way to AI, right? I think I messed up the notation here, but hopefully it shouldn't be too hard to understand. So this is I, the last element, and then there's another AJ, right, in here, where this sum is maximum for any subarray that ends at AI. So if I find, for example, AJ minus 1, this sum is going to always be less than or equal to the sum from AJ to AI, right? Okay, so this is what VI. So this one here is VI, the maximum sum. Okay, so how can I calculate VI? Well, VI, okay, let's visualize it. Let's try to visualize it, okay? So I know that all the way to AI minus 1, AI, okay. I know that my largest contiguous subarray ending at AI should include AI, right? So, because it ends at AI, right? That's the only thing I know. It includes AI, right? This element must be in it. So let's think about what ways this element might be in the array. Well, one possible way is it's included in a bigger array, right? So there's some AK here, right? That where this element here is the maximum sum, right? So there's a K, right? There's a K such that VI is equal to the sum of AK all the way to AI, right? That's one possible way. And here K is less than I, right? Strictly less than I, not equal to I. Another idea is K is equal to I. So there's two cases, right? Either K is less than I or K is equal to I. So if K is equal to I, then simply VI is equal to AI, right? The maximum from A1 to AI ending at AI is just simply this element. So when would this happen? Let's say we have a -1, -2, -3, and 1, right? This one over here doesn't need any of these elements, right? Because this array would be -2. This array would be -4. This array here would be -5. So why do we need these elements here? Let's just ignore them and take this element on its own. So that's the case when K is equal to I. However, if K is less than I, then we simply know that we want the maximum sum ending at AI, right? But we know that k is less than I, so we can write this as vi is equal to the sum of ak all the way to ai minus 1 plus ai, right? But hold on a second, this sum over here is the maximum sum for vi minus 1. So this term here is vi minus 1 plus ai. So in other words, we have that vi is equal to the maximum of either ai or vi minus 1 plus ai, okay? Now we can compute this in O1 time, and this whole process here takes O of n, because there are I ranges from n and it's bigger than or equal to 1, right? So this whole process takes O of n time. So this whole process here takes O of n times O of 1, which is equal to O of n time. So the whole process takes O of n time. But hold on a second here. You might think there's something fishy here, right? Because when I defined vi, I defined vi as the maximum sum of a contiguous subarray from elements 1 to I, but ending at ai, right? I said it has to end at ai. But in the problem, in the original problem, so if I just return vn, then that means it's a maximum sum of the contiguous subarray from elements 1 to n, but ending at an. What if the maximum subarray actually ends at, an minus 1 or an minus 2, right? What if the maximum subarray actually ends here and not here? So actually vn is not my answer. So how can I use vn to reach my answer? Well, we can simply return the maximum sum of a contiguous subarray from elements 1 to 1, or from elements 1 to 2, or from elements 1 to 3, or from elements 1 to 4, all the way to from elements 1 to n. In other words, my solution to my original problem is given by v of n is equal to the maximum, or my solution here, so I shouldn't say, so solution is equal to the maximum of v1, v2, all the way to vn. Okay, so let's recap really quickly. We said that vi is the maximum sum, contiguous sum of a sum, so the maximum subarray, contiguous subarray sum ending at element ai, okay? We also said that vi has the recurrence maximum of vi minus 1 plus ai, or simply ai. We also said that our end solution, so end solution, should be the maximum of v1 all the way to vn. Okay, so how do we write this in pseudocode? We say, okay, let v1 to n be an empty array, right? And then we're going to say, okay, v1 is equal to a1, right? If there's only one element, then simply the maximum sum is a1. And then I'm going to say, okay, for I2 to n, what do? I say vi is equal to the maximum of vi minus 1 and plus ai and ai. Okay. Now, when I'm done here, then once I'm done with this process, then I return the maximum element of v, and that's my solution. So this process over here takes O of n time, this process takes O1, and hopefully you know that returning the maximum element actually takes only O of n time. So the whole algorithm ends up taking an O(n) time. So we've basically reduced the running time of the brute force method from an O(n) cubed to an even O(n) squared if you want, all the way down using dynamic programming to an O of n solution. So thank you for watching the video. If you have any questions, let me know in the Q&A section. So until the next video, happy coding.